Theoretical Foundations of t-SNE for Visualizing High-Dimensional Clustered Data T. Tony Tai, Rongma Editor, Jiju Abstract. This paper investigates the theoretical foundations of the T-distributed stochastic neighbor embedding t-SNE algorithm, a popular nonlinear dimension reduction and data visualization method. A novel theoretical framework for the analysis of t-SNE based on the gradient descent approach is presented. For the early exaggeration stage of t-SNE, we show its asymptotic equivalence to power iterations based on the underlying graph Laplacian, characterize its limiting behavior, and uncover its deep connection to Laplacian spectral clustering, and fundamental principles including early stopping as implicit regularization. The results explain the intrinsic mechanism and the empirical benefits of such a computational strategy. For the embedding stage of t-SNE, we characterize the kinematics of the low-dimensional map throughout the iterations and identify an amplification phase, featuring the intercluster repulsion and the expansive behavior of the low-dimensional map, and a stabilization phase. The general theory explains the fast convergence rate and the exceptional empirical performance of t-SNE for visualizing clustered data, brings forth the interpretations of the t-SNE visualizations, and provides theoretical guidance for applying t-SNE and selecting its tuning parameters in various applications. Keywords: clustering, data visualization, foundation of data science, nonlinear dimension reduction, t-SNE. 1. Introduction. Data visualization is critically important for understanding and interpreting the structure of large datasets, and has been recognized as one of the fundamental topics in data science. A collection of machine learning algorithms for data visualization and dimension reduction have been developed. Among them, the T-distributed stochastic neighbor embedding t-SNE algorithm, proposed by van der Maten and Hinton, 2008, is arguably one of the most popular methods and a state-of-art technique for a wide range of applications. Specifically, t-SNE is an iterative algorithm for visualizing high-dimensional data by mapping the data points to a two- or finite-dimensional space. It creates a single map that reveals the intrinsic structures in a high-dimensional dataset, including trends, patterns, and outliers, through a nonlinear dimension reduction technique. In the past decade, the original t-SNE algorithm, along with its many variants, has made profound impact to the practice of scientific research, including genetics, molecular biology, single-cell transcriptomics, computer vision, and astrophysics. In particular, the extraordinary performance of t-SNE for visualizing high-dimensional data with intrinsic clusters has been widely acknowledged. Compared to the extensive literature on the computational and numerical aspects of t-SNE, there is a paucity of fundamental results about its theoretical foundations. See Section 1.3 for a brief overview. The lack of theoretical understanding and justifications profoundly limits the user's interpretation of the results, as well as the potentials for further improvement of the method. This paper aims to investigate the theoretical foundations of t-SNE. Specifically, we present a novel framework for the analysis of t-SNE, provide theoretical justifications for its competence in dimension reduction and visualizing clustered data, and uncover the fundamental principles underlying its exceptional empirical performance. 1.1 Basic t-SNE Algorithm. Let xi 1 less than or equal to I less than or equal to n be a set of p-dimensional data points. t-SNE starts by computing a joint probability distribution over all pairs of data points, xi 1 less than or equal to I less than or equal to n, represented by a symmetric matrix. P equals pi 1 less than or equal to ij less than or equal to n in Rn's n, where pi I equals 0 for all 1 less than or equal to I less than or equal to n, and for I equals j, see formula. Here tau I are tuning parameters, which are usually determined based on a certain perplexity measure and a binary search strategy. Similarly, for a two-dimensional one-map yi1 less than or equal to I less than or equal to nr2, we define the joint probability distribution over all pairs yi yj, 1 less than or equal to I equal to j less than or equal to n through a symmetric matrix. Q equals to qij 1 less than or equal to ij less than or equal to n, where qi equals to 0 for all less than or equal to I less than or equal to n, and for I equal j, see formula. Intuitively, P and Q are similarity matrices summarizing the pairwise distances of the high-dimensional data points xi1 less than or equal to I less than or equal to n, and the two-dimensional map yi1 less than or equal to I less than or equal to n, respectively. Then t-SNE aims to find yi1 less than or equal to I less than or equal to n that minimizes the KL divergence between P and Q, that is, see Formula 1. Throughout, we focus on the two-dimensional embedding for ease of presentation. However, all the theoretical results obtained in this work holds for any finite constant embedding dimension. Theoretical foundation of t-SNE. Many algorithms have been proposed to solve this optimization problem. The most widely used algorithm was proposed in van der Motten and Hinton, 2008, which draws on a variant of gradient descent algorithm with an updating equation see formula, where h in R plus is a pre-specified step size parameter, see formula, R2 is the gradient term corresponding to yi with see formula R, and mk in R plus is a pre-specified momentum parameter. The algorithm starts with an initialization y0i equals y minus 1i for I in 1, 2n, drawn independently from a uniform distribution on minus 0.01, 0.2, or from n0 the 2i for some small delta 0. As indicated by van der Motten and Hinton, 2008, the inclusion of the momentum term mk plus 1 yki minus 1i in 4 is mainly to speed up the convergence and to reduce the risk of getting stuck in a local minimum. In this paper, for simplicity and generality, we focus on the basic version of the t-SNE algorithm based on the simple gradient descent, with the updating equation y of k plus 1 I equals y of ki plus hd at ki for I equals 1 n. 5. In van der Motten and Hinton, 2008, and van der Motten, 2014, the recommended total number of iterations is 1,000, while the step size h is initially set as 400 or 800, and is updated at each iteration by an adaptive learning rate scheme of Jacobs, 1988. The standard gradient descent algorithm, as in 5, suffers from a slow convergence rate and even non-convergence in some applications. As an amelioration, van der Motten and Hinton, 2008, proposed an early exaggeration technique, applied to the initial stages of the optimization, that helps create patterns in the visualization and speed up the convergence. Such a computational strategy has been standard in practical use. In fact, most of the current software implementations of t-SNE are based on an early exaggeration stage followed by an embedding stage that iterates a certain gradient descent algorithm. In our setting, these two stages can be summarized as follows. Early exaggeration stage. For the first k0 and 0 iterations, the pi-j's in the gradient term d of ki are multiplied by some exaggeration parameter av of right and 0. So the updating equation for this early exaggeration stage becomes C formula, where C formula in R and the factor 4 in dki is absorbed into the step size parameter h. We refer to this first stage of the t-SNE algorithm as the early exaggeration stage. In van der Motten and Hinton, 2008, the authors choose f equals 4 and k50 for the early exaggeration stage, whereas later in van der Motten, 2014, it is recommended that alpha equals 12 and k0 equals 250. In particular, it is empirically observed that the early exaggeration technique enables t-SNE to find a better global structure in the early stages of the optimization by creating very tight clusters of points that easily move around in the embedding space. This observation is later supported by some pioneering theoretical investigations, see section 1.3. Nevertheless, there are interesting questions to be answered concerning I, the underlying principles and mechanism behind such a computational strategy, 2. The limit behavior of the low-dimensional map, how sensitive is the performance of t-SNE with respect to the choice of tuning parameters, alpha, h, k0, and IV, how to efficiently determine these parameters to achieve the best empirical performance. Figure 1, an illustration of the t-SNE iterations that visualize samples from the MNIST dataset, section 5. Each sample corresponds an image of handwritten digit 2, 4, 6, or 8. The visualizations are obtained using the RTSN function in the R package RTSN by selecting the exact t-SNE mode, theta p equals f, dropping the momentum terms, momentum equals 0, final momentum equals 0, and setting perplexity 30 default, av equals 12 default, h equals 200 default in 6, and k0 equals 40. The first three plots, top row, correspond to the early exaggeration stage, while the last three plots, bottom row, correspond to the embedding stage. Embedding stage. After the early exaggeration stage, the exaggeration parameter alpha is dropped, and the original iterative algorithm, 5, is carried out till attaining a pre-specified number of steps. We refer to this second stage as the embedding stage. The final output is a two-dimensional map yk1i1 less than or equal to I less than or equal to n, commonly treated as a low-dimensional embedding of the original data, xi1 less than or equal to I less than or equal to n, expected to preserve its intrinsic geometric structures. In addition to data visualization, t-SNE is sometimes also used as an intermediate step for clustering, signal detection, among many other purposes. In particular, it has been observed that when applied to high-dimensional clustered data, t-SNE tends to produce a visualization with more separated clusters, which are often in good agreement with the clusters found by a dedicated clustering algorithm. See Figure 1 for an example of data visualization using such a basic t-SNE algorithm. 1.2 Main results in our contribution. A formal theoretical framework is introduced for the analysis of t-SNE that relies on a joint statistical and computational analysis. The key contribution of the present work can be summarized as follows. We rigorously establish the asymptotic equivalence between the early exaggeration stage and power iterations. Our theory unveils novel properties such as the implicit regularization effect and the necessity of early stopping in the early exaggeration stage for weakly clustered data. We characterize the behavior of t-SNE iterations at the embedding stage by identifying an amplification phase along with its intercluster repulsion and expansion phenomena and a stabilization phase of this stage. We give the theoretical guidance for initialization and selecting the tuning parameters at both stages in a flexible and data-adaptive manner. We provide practical advice on applying t-SNE and interpreting the t-SNE visualizations of high-dimensional clustered data. The main results can be explained in more detail from three perspectives. Early exaggeration stage. Through a discrete time analysis, sections 2.1 and 2.2, we establish the asymptotic equivalence between the early exaggeration stage and power iterations based on the underlying graph Laplacian associated with the high-dimensional data, providing a spectral graphical interpretation of the algorithm. We show the implicit spectral clustering mechanism underlying this stage, which explains the adaptivity and flexibility of t-SNE for visualizing clustered data without specifying the number of clusters. Specifically, for the cases where xi1 less than or equal to I less than or equal to n are approximately clustered into R groups, we make the key observation that the coordinates of y of ki1 less than or equal to I less than or equal to n converge to the R-dimensional Laplacian null space, leading to a limiting embedding where the elements of y of ki1 less than or equal to I less than or equal to n are well clustered according to their true cluster membership. On the other hand, through a continuous time analysis, section 2.3, we study the underlying gradient flow and uncover an implicit regularization effect depending on the number of iterations. In particular, our analysis implies that when dealing with noisy and approximately clustered data, one should stop early in the early exaggeration stage to avoid overshooting. These results justify the empirical observations about the benefits of the early exaggeration technique in creating cluster structures and speeding up the algorithm. For more details about comparison with the existing results, see Section 1.3 and the discussions after Corollary 7 in Section 2. Embedding stage. We provide a mechanical interpretation of the algorithm by characterizing the kinematics of the low-dimensional map at each iteration. Specifically, in Section 3, we identify an amplification phase within the embedding stage, featuring the local intercluster repulsion, Theorem 13, and the global expansive behavior, Theorem 15, of yki1 less than or equal to I less than or equal to n. In the former case, it is shown that the movement of each yki to yk plus 1i is jointly determined by the repulsive forces pointing toward yki from each of the other clusters, Figure 2. That amounts to increasing spaces between the existing clusters. In the latter case, it is shown the diameter of y of ki1 less than or equal to I less than or equal to n may strictly increase after each iteration. We observe that following the amplification phase, there is a stabilization phase where y of k ijek1 less than or equal to I less than or equal to n is locally adjusted to achieve at a finer embedding of xi1 less than or equal to I less than or equal to n. These results together explain the fast convergence rate and the exceptional empirical performance of t-SNE for visualizing clustered data. The articulation of these phenomena also leads to useful practical guidances. See below and remark 16 in section 3 for more details. Figure 2. Illustration of the intercluster repulsion where the original data xi1 less than or equal to I less than or equal to n have 3 clusters. The position of y of k plus 1i is jointly determined by y of ki and 2 repulsive forces fki1 and fki2 pushing y ki away from the other 2 clusters. Practical implications. The general theory brings forth the interpretations of the t-SNE output and provides theoretical guidance for selecting tuning parameters and for initialization. In section 4, we illustrate the general theory on 2 examples of high-dimensional clustered data, one generated from a Gaussian mixture model and another from a noisy nested sphere model. We also analyze in section 5 a real-world dataset to further demonstrate the practical implications of our theory. In particular, our analysis allows for a wider spectrum of tuning parameters, figure 10 and equation 39, and initialization procedures than those considered in previous theoretical works. Moreover, our theoretical results support the state-of-art practice, but also lead to novel insights, e.g. the first item below, that has been unknown to our knowledge. In the following, we summarize our general advice on applying t-SNE to potentially clustered data. Theoretical foundation of t-SNE. For weakly clustered data, one may adopt the early exaggeration technique, but needs to stop early. For example, set k0 equals log n2 to avoid overshooting. Failure of stopping early may lead to false clustering. See figure 5 below for an illustration. t-SNE visualization based on random initialization and early exaggeration is reliable in terms of cluster membership, but not relative position of clusters. For example, the neighboring clusters in visualization may not be interpreted as neighboring clusters in the original data. See figure 6 below for an illustration. Occasionally, false clustering may appear as an artifact of random initialization and intercluster repulsion. Therefore, it is helpful to run t-SNE multiple times to fully assess the effect of random initialization. See figure 6 below for an illustration. For strongly clustered data, one can speed up the algorithm by replacing the early exaggeration stage by a simple spectral initialization 2, where y01, y02 are the eigenvectors associated with the smallest 2 eigenvalues of LP. 1.3 Related work. The impressive empirical performance of t-SNE has recently attracted much theoretical interests. Lee and Verlason, 2011, investigated the benefits of the so-called shift invariant similarities used in the stochastic neighbor embedding and its variants. Later on, they further identified 2 key properties of these visualization methods. In Shaham and Steinerberger, 2017, a large family of methods, including t-SNE as a special case, were studied and shown to successfully map well-separated disjoint clusters from high dimensions to the real line so as to approximately preserve the clustering. In Aurora et al., 2018, a theoretical framework was developed to formalize the notion of visualizing clustered data, which is used to analyze the early exaggeration stage of t-SNE and to justify its high visualization quality. Linderman and Steinerberger, 2019, showed that in the early exaggeration stage of t-SNE, with properly chosen parameters alpha and h, a subset of the 2-dimensional map belonging to the same cluster will shrink in diameter, suggesting well-clustered visualization following iterations. We note that connections between the early exaggeration stage and power iterations have been pointed out in Aurora et al., 2018, and Linderman and Steinerberger, 2019, but the discussions therein are mostly informal and heuristic. In contrast, we provide rigorous theoretical justification for such a connection, identify its condition, and explicate its consequences. By extending the idea of t-SNE, Im et al. 2018 considered a class of methods with various loss functions based on the F divergence, and theoretically assessed the performances of these methods based on a neighborhood-level precision recall analysis. More recently, Zhang and Steinerberger, 2021, proposed to view t-SNE as a force-based method which generates embeddings by balancing attractive and repulsive forces between data points. In particular, the limiting behavior of t-SNE was analyzed under a mean field model where a single homogeneous cluster is present. At the empirical side, the recent works of Kobach and Behrens 2019 and Kobach and Linderman 2021 summarize the state-of-art practice of using t-SNE to biological data. A comprehensive survey of existing data visualization methods and their properties can be found in Nonato and Aupetit 2018. Despite these pioneering endeavors, the theoretical understanding of t-SNE is still limited. Many intriguing phenomena and important features that arise commonly in practice have not been well understood or properly explained. Moreover, it remains unclear how to properly interpret the t-SNE visualization and its potential artifacts. These important questions are carefully addressed in the current work for the case of clustered data. Compared to the existing works, the theoretical framework developed in our work leads to identification and explication of novel properties, phenomena, and important practical implications on t-SNE, as summarized at the beginning of section 1.2. 1.4. For a vector A equal A1A in Rn, we denote diag A1 AN in Rn ties n as the diagonal matrix whose ith diagonal entry is AI, and define the p-norm, see formula. For a matrix A equals Aij in Rnz, we define its Frobenius norm as see formula, its Eamheim's norm as A equals max 1 less than or equal to Ij less than or equal to n Aij, and its spectral norm as A equals subs x2 less than or equal to 1 ax2. We also denote AI in Rn as its ith column and AI in Rn as its ith row. Let Onk equals V in Rn times k, Vh V equals Ik be the set of all n times k orthonormal matrices, and On equals Onn, the set of n-dimensional orthonormal matrices. For a rank R matrix A in Rn Rn's n with 1 less than or equal to R less than or equal to n, its eigendecomposition is denoted as A equals U1, where U and On are with its columns being the eigenvectors, and Gang equals diag, Laglan 1A, Laglan 2A, Laglan Ra, with Laglan min A equals Le1A less than or equal to Laglan A equals a max A, being the ordered eigenvalues of A. For a smooth function f of x, we denote moid f of x equals df dx, and plef fx is d2ff dx2. For any integer n0, we denote the set n equals 1 to n. For a finite set S, we denote its cardinality as at S. For a subset S star n, we define its diameter dimes equals sup x y and s y min f2. For sequences n and bn, we write n equal bn or n bn if lim n and bn equal to 0, and write n equal bn, and monosh bn or bn x an if there exists a constant c such that n less than or equal to cbn for all n. We write an out bn and an anosh bn. Throughout, C, C1, C2 are universal constants that can vary from line to line. The rest of the paper is organized as follows. Section 2 presents the theoretical analysis for the early exaggeration stage of t-SNE. Section 3 analyzes the embedding stage. The general theory is then applied in Section 4 to two specific settings of model-based clustered data, one under a Gaussian mixture model and another under a noisy nested sphere model. Analysis of a real-world dataset is presented in Section 5. Section 6 discusses potential applications, extensions, and other related problems. Proofs of our main results and supplementary figures are collected in Appendix A to F. 2. Analysis of the early exaggeration stage. 2.1 Asymptotic graphical interpretation and localization. We start with a key observation that connects the updating equation 6 to some graph-related concepts. To this end, we introduce the following definition. Definition 1, degree and Laplacian operators. For a symmetric matrix, A equals Aij1 less than or equal to Ij less than or equal to n in Rnz, define the degree operator D, Rnz by dA equals diag, Pni equals 1ai1, Pni equals 1n, and the Laplacian operator L, Rnz by L of A equals dA and Z. We define S of Ki equals S of Ki Jaffer, 1 less than or equal to Ij less than or equal to n in Rnz, with Ski and 0 for all I in n. Then we can rewrite the updating equation 6 using the matrix form as C formula, where in Rn times n is the identity matrix, and y of k in Rn consists of the ath coordinates of y1 less than or equal to I less than or equal to n. As a consequence, for each iteration k, if we treat the symmetric matrix Sk alpha as the adjacency matrix of a weighted graph G k with n nodes that summarizes the pairwise relationships between n data points I1 less than or equal to I less than or equal to n, equation 7 has an interpretation that links to the Laplacian matrix of such a weighted graph. To better understand the meaning and the properties of the underlying graph G of k that evolve over iterations, we take a closer look at its adjacency matrix Sk alpha. In particular, one should keep in mind that in common applications of t-SNE, the early exaggeration stage has the following empirical features. I, moderate or relatively large values of the exaggeration parameter alpha, default 12 in the R package are t-SNE. I, local initializations y0, I1, less than or equal to I less than or equal to n around the origin, see section 1.1, and relative small diameters diam yki1 less than or equal to I less than or equal to n over the iterations, figure 1. Our next result shows that these empirical features of t-SNE have deep connections to the asymptotic behavior of the evolving underlying graphs and their adjacency matrices Sk af k greater than or equal to 1 in the large sample limit as n pi. Theorem 2. Asymptotic graphical interpretation. Recall that p equals pi j1 less than or equal to ij less than or equal to n is defined in 1, and denote I of k equals diam y of ki 1 less than or equal to I less than or equal to n. 2. Then for any I j in n with I spike equals j, and each k greater than or equal to 1 such that k11, we have C formula. Consequently, if we denote 1n equals 1, 1i in Rn, and hn equals 1n, n minus 1, 1n, 1n minus n, then for each k greater than or equal to 1, as long as y of k alpha satisfies C formula, we have C formula. The above theorem implies that for large n, as long as the diameter of y of k, I let 1 less than or equal to I less than or equal to n, remains sufficiently small, and the exaggeration parameter alpha sufficiently large, the adjacency matrix Sk alpha behaves almost like a fixed matrix alpha to phn across the iterations. In other words, we may treat the updating equation 7 as an approximately linear equation, C formula, where the linear operator in minus hl alpha p minus hn only relies on the Laplacian of a fixed weighted graph whose adjacency matrix is given by the scaled and shifted similarity matrix alpha p minus hn. This essentially opens the door to our key result on the asymptotic equivalence between the early exaggeration stage and power iterations. Before we formally present such a result, we need to first point out an important phenomenon concerning the global behavior of the low-dimensional map at the early exaggeration stage. Specifically, we make the following assumptions on the initialization and the tuning parameters AVA, H, K. See formula? Intuitively, condition I1 says that the initialization y of 0 I1 less than or equal to I less than or equal to n should not be simply all zeros are unbounded, whereas the condition T1 as a consequence of 8 essentially requires the cumulative deviations of HL of K alpha from HL of P minus HN to be bounded. Our next result shows that, under these assumptions, the diameter of y of k I1 less than or equal to I less than or equal to n may not increase throughout the iterations, so the embedding remains localized within the initial range. Proposition 3, localization. Suppose I1 and T1 hold. We have C formula for some universal constant C blib 0. The above proposition confirmed the globally localized and non-expansive behavior of y of k I1 less than or equal to I less than or equal to n over the early exaggeration stage observed in practice, figure 1. Concerning theorem 2, it tells us the step-specific condition I of k, n lac p input 0, therein can be generalized to all finite k's as long as the initialization y of 0 I1 less than or equal to I less than or equal to n is concentrated around 0, that is, max in y of 0, ev, lace 2, p, alf n p. Furthermore, when alpha h are chosen such that the stepwise deviation diminishes, i.e. Rn h half byte of p plus h0, proposition 3 indicates that 10 may remain true for even larger numbers of iterations as long as k equals OR minus 1n. 2.2 Asymptotic power iterations. Implicit spectral clustering and early stopping. With the above graphical interpretation of the updating equation 7 in mind, we now present our key result concerning the asymptotic equivalence between the early exaggeration stage and a power method based on the Laplacian matrix LHN. In particular, we make the following assumptions on the initialization and the tuning parameters. I2, y of 0, I1 less than or equal to I less than or equal to n satisfies max AO in y of 0 determined equal to O and of p n peta my flee as n polite d. The parameters a h k satisfy av n minus 1 and k h av p n h h by n equal to O1 as n peta. Condition I2 follows from the discussion subsequent to proposition 3, which along with condition T1d, which is analogous to but stronger than T1, ensures the conditions for Theorem 2 and Proposition 3 to hold simultaneously. Theorem 4, asymptotic power iterations. Under conditions I1, I2, and T1d, we have 10 and 12 hold, and so does the asymptotic equivalence, see formula. The above theorem suggests that each step of the early exaggeration stage may be treated as a power method in the sense that, see formula. The normalization by y of 0, ep2 in 13 makes sure the result to be scale invariant to the initialization. It is well known that for a fixed matrix G in Rnn with 1 as its unique largest eigenvalue in magnitude, the power iteration yk equals gky0 converges to the associated eigenvector as k Fogli. As a result, when treated as an approximate power method, the early exaggeration stage of t-SNE essentially aims to find the direction of the leading eigenvector of the matrix in Ms LP Ms Hn, which, as will be shown shortly, is actually equivalent to finding the eigenvector associated with the smallest eigenvalue of the graph Laplacian ELV af p minus Hn, or the null space of ELV p. Led by these observations, our next results concern the limiting behavior of the low-dimensional map y of ki1 less than or equal to I less than or equal to n as the number of iterations k of t. Note that any Laplacian matrix has an eigenvalue 0 associated with a trivial eigenvector n-121. Given the affinity 14 between t-SNE and the power method, we start by showing that the linear operator minus hl of p minus hn k would converge eventually to a projection operator associated with the null space of the Laplacian LP. In particular, we let r greater than or equal to 1 be the dimension of the null space of the Laplacian LP in Rn's n, and assume T2 the parameters av h satisfies key h ln r plus 1 LFP less than or equal to h ln n LFP 1 for some constant key in 0, 1. This assumption corresponds to the so-called eigengap condition in the random matrix literature, which gives the signal strength requirements for the recovery of the eigenvalues eigenvectors, and in the meantime the conditions for the tuning parameters. Theorem 5, convergence of power iterations, let U in OR, such that its columns consist of an orthogonal basis for the null space of L of P. Suppose KH equals ON and T2 hold. Then we have C formula. Combining theorems 4 and 5, we know that for sufficiently large n and k, the t-SNE iterations y of k array may converge to the projection of the initial vectors y0, x0 into the null space of the Laplacian LP, that is, C formula. Now, to better understand the above theorem and its implications on the limiting behavior of t-SNE applied to clustered data, we study the null space of a special class of Laplacian matrices, corresponding to the family of weighted graphs consisting of r greater than or equal to 2 connected components. In fact, when the original data xi1 less than or equal to I less than or equal to n are well clustered and tau i's are appropriately chosen, the family of disconnected weighted graphs arise naturally since their adjacency matrices are good approximations of P based on these data. We illustrate this point further in section 4. In the following, we say a symmetric adjacency matrix P is well conditioned if its associated weighted graph has R greater than or equal to 2 connected components. Our next result characterizes the Laplacian null space corresponding to these disconnected weighted graphs. Proposition 6, Laplacian null space. Suppose A in Rnn is symmetric and well-conditioned. Then the smallest eigenvalue of the Laplacian LA is 0 and has multiplicity R, and the associated eigensubspace is spanned by theta R, where for each R in 1 R, see formula, and nr is the number of nodes in the rth-connected component. In particular, up to possible permutation of coordinates, any vector u in the null space of LA can be expressed as C formula for some A1 AR in R. From the above proposition, for a well-conditioned matrix, the components of any u in the Laplacian null space has at most R distinct values, and whenever A1 AR equals R, The coordinates share the same value if and only if the corresponding nodes fall in the same connected component, i.e., the same cluster. Combining 16 and 17, one can see that, for strongly clustered data, the output from the early exaggeration stage essentially converges to the eigenvectors associated with the Laplacian null space. This leads to our fourth practical advice at the end of section 1.2. We now generalize the analysis to the setting where the data xi1 less than or equal to I less than or equal to n is only weakly clustered in the sense that there exists a well-conditioned symmetric matrix P under close to P under properly chosen tau I, and the underlying graph associated with P may not be necessarily disconnected. More specifically, we assume T2D there exists a symmetric and well-conditioned matrix P twice in Rn tan n satisfying T2, and is sufficiently close to P in the sense that A of L of P equal 0,1. For a given P satisfying T2D, let NR with R in R be the size of the rth connected component in the graph associated with P psi. Our next theorem obtains the implicit spectral clustering and early stopping properties of the early exaggeration stage. Theorem 7, implicit clustering and early stopping. Suppose the similarity P and the tuning parameters AVA H, K satisfy T1.D and T2D, and the initialization satisfies I1 and I2. Then there exists some permutation matrix O in Rn's n such that for ed_n, see formula, where see formula ape square root of nr for R in R. Theorem 7 describes the limiting behavior of the low-dimensional map y of ki1 less than or equal to I less than or equal to n as nk3 when the original data is approximately clustered. Specifically, elements from y of ki1 less than or equal to I less than or equal to n associated with a connected component of the underlying graph would converge cluster-wise towards a few points on R2. In particular, Theorem 7 suggests that, at the end of the early exaggeration stage, although the samples belonging to the same underlying cluster tend to be clustered together in the t-SNE embeddings, the cluster centers of the t-SNE embeddings only rely on the initialization rather than the actual positions of the underlying clusters. Therefore, if initialized randomly and non-informatively, the t-SNE embeddings at the end of the early exaggeration stage tend to preserve only the local structures, i.e., the closeness of the samples from the same cluster, but not the global structures, i.e., the relative positions of different clusters, of the original data. This observation, as illustrated in Figure 6, leads to our second practical advice at the end of section 1.2. Our theory refines and improves the existing works such as Linderman and Steinerberger, 2019, and Aurora et al., 2018, in various aspects. Firstly, our theoretical framework formalizes and explains the asymptotic equivalence between the early exaggeration stage and the power iterations. The theory provides a precise description of the limiting behavior of the low-dimensional map and the theoretical conditions. Secondly, unlike the previous works where only one particular initialization and relatively limited range of tuning parameters were considered, our analysis yields general conditions and allows for more flexible choices of the initialization procedures and tuning parameters. Finally, our analysis unveils the need of stopping early in the early exaggeration stage for weakly clustered data, which is a novel feature. Specifically, both conditions, T1.D and T2.D, but in a controlled manner whenever points L, P minus P equals 0, there is a data-dependent upper bound on the iteration number, see formula, which becomes more stringent for weakly clustered data, I not too small. Such a phenomenon is also observed empirically, Figure 5, where failing to stop early would lead to false clustering. 2.3 Gradient flow and implicit regularization for in1,2. Let prize yk greater than or equal to 0 be the sequence defined by the power iterations yk equals in minus hf p minus hn ky0 e. Theorem 4 shows that presh ykk greater than or equal to 0 well approximates the t-SNE iterations ykk greater than or equal to 0 in the large sample limit. The sequence yk ek greater than or equal to 0 admits the updating equation, see formula, with an initial value y of 0, treating a 20 as an auxiliary gradient descent algorithm to the original algorithm, 7, a continuous time analysis can be developed accordingly, which yields interesting insights about the t-SNE iterations, yk ek greater than or equal to 0. We begin by modeling yk greater than or equal to 0 by a smooth curve y of t with the ansatz y of ka approximately equal to y of kh. Define a step function y h at t equals y of yka for kh less than or equal to tk plus 1h, and as h0, y h of t approaches y of t satisfying C formula A. The above first-order differential equation 21 is usually referred as the gradient flow associated with the power iteration sequence y of ka greater than or equal to 0, whose limiting behavior can be studied through the step function yh at t. The following theorem provides a non-asymptotic uniform upper bound on the deviation of yht from t over t in 0t, and that of ykh from y over k less than or equal to t for h. Proposition 8, gradient flow. For at what equals 1, 2, and any given t or 0, we have C formula, where y(ht) is the continuous time step process of y(ka) generated by 20, and y is the solution to the ordinary differential equation 21. As a consequence, for t equals hk, if kh2 L of p minus hm minus 2 as 2, 0, then for a in 1, 2, see formula. Combining theorems 4 and 8, we obtain the approximation yk approximately equal to ykh over a range of k greater than or equal to 0 for properly chosen parameters ava hk and initialization. Consequently, the properties of the solution path y at t may provide important insights on the behavior of the t-SNE iterations at the early exaggeration stage. We start by stating the following proposition concerning the explicit expression of y of t. Proposition 9, solution path. For at in 1, 2, the first-order linear differential equation 21, with initial value y of 0 equals y of 0, has the unique solution y of t equals xtl of hn. y0 may is the matrix exponential defined as, see formula. In particular, suppose L of p have the eigendecomposition L of p equals p equal 1 nu I uii, where 0 equals lemlod 1 less than or equal to lemlod n, and u1 equals n minus 121n. Then we also have C formula. Several important observations about the solution path y at t can be made. Firstly, by proposition 9, for u1 um, where m and n is the largest integer such that aval m less than or equal to 1 n minus 1, we have C formula. This can be treated as a continuous version of the limiting behavior of the power iterations obtained in Theorem 5. Under the conditions of Theorem 5, we have aval less than or equal to 1 n minus 1 for all m in R, but aval r plus 1 of 1 n minus 1, so that 25 implies that y of t converges to the null space of L of p. Secondly, as long as t equals on by orthogonality of ui, we have C formula. The right-hand side is monotonically non-increasing in t. Hence, the average distance of the rows in y1hk, y2hk to the origin remains non-expansive over the iterations and is bounded up to a constant by that of y10, y20. This result echoes proposition 3 based on the discrete time analysis. The third and more insightful observation from 24 is its implications on the finite time behavior of the original t-SNE sequence, y of kk greater than or equal to 1, which complements our discrete time analysis. Specifically for finite t brings 0, the coefficient of the ith basis ui in yt is proportional to e minus I, which is non-increasing in I. Consequently, 24 implies that in the early steps of the iterations, the t-SNE algorithm imposes an implicit regularization effect on the low-dimensional map yki1 less than or equal to I less than or equal to n in the sense that C formula. Comparing to the limit 25, or 16, during the early steps of the iterations, y of kx is regularized as a conical sum of all the eigenvector basis ui1 less than or equal to I less than or equal to n, with larger weights on the eigenvectors ui corresponding to the smaller eigenvalues of L of p, and smaller weights on those corresponding to the larger eigenvalues of L of p. As the iteration goes, the contributions from the less informative eigenvectors with larger eigenvalues lambda I, such that avalet I led I to 1 n minus 1 decrease exponentially in k, whereas the contributions from the more informative eigenvectors with smaller eigenvalues lambda I, such that avalet I to 1 n minus 1 increase with k. Importantly, the inclusion of all the eigenvectors helps to better summarize the cluster information in the original data and to avoid convergence to the trivial eigenvector n minus 1 mar 21n. Indeed, the convergence 25 by itself may not lead to a cluster structure in the limit, as in many applications with weakly clustered data, the graph corresponding to P may be simply connected under finite samples, so that the null space span U1, UM is effectively the one-dimensional space spanned by n-1/21 alone. However, as our next theorem shows, the benefit of the implicit regularization brought about by stopping early at the exaggeration stage can be seen in the creation of desirable clusters in YKI1 less than or equal to I less than or equal to n for weakly clustered data with approximately block-structured P. In particular, we make the following assumptions analogous to T1.d and T2d in the discrete time analysis. The parameters of ht satisfy of n leb r plus 1 minus 1 and t equals on as n phone. T2c there exists a symmetric and well-conditioned matrix P on and n such that len r plus 1 L want max T of minus 1 L minus P and epsilon minus P equals O1 as n as Fadhade. Similar to the previous conditions, T1c and T2.c concerns the approximate block structure of P and ensures sufficient exaggeration and early stopping of the iterations. Theorem 10, implicit regularization, clustering, and early stopping. Under conditions I1c and T2.c, let Udin OR such that its columns span the null space of P'. Then we have C formula, and for Z defined in Theorem 7, there exists a permutation matrix O in Rn as n such that C formula. An immediate consequence of the above theorem is the following corollary, which arrives at the same conclusion as Theorem 7 through a different route. Corollary 11. Suppose the conditions of Theorems 4 and 10 hold with T hk and k ivern 2 h2 at P minus hn 2 0. Then the conclusion of Theorem 7 holds. The above theorems provide a deeper theoretical explanation of the need of stopping early at the exaggeration stage. On the one hand, the number of iterations should be sufficiently large so that y of k, I1 less than or equal to I less than or equal to n, moves away from the initialization and is sufficiently close to a subspace where the underlying cluster information is properly stored. On the other hand, the iterations should be also stopped early for weakly clustered data to avoid overshooting, that is, convergence to the null space of the superficial Laplacian L of P, which may only include the non-informative trivial eigenvector n-21n, figure 5 right. 3. Analysis of the embedding stage. We have shown in section 2 that the iterations in the early exaggeration stage essentially create clusters in the low-dimensional map y of k, I1, less than or equal to I less than or equal to n, that agree with those underlying xi1 less than or equal to I less than or equal to n. However, as indicated by proposition 3, so far the low-dimensional map is concentrated and localized around 0, which may not be ideal for visualization purpose. In addition, by Theorem 7, much information about xi1 less than or equal to I less than or equal to n, other than its cluster membership, are not reflected by the low-dimensional map. In this section, we show that after transition to the embedding stage, the t-SNE iterations 5 essentially start by amplifying and refining the existing cluster structures in the low-dimensional map and then aim at a proper embedding of the original data. We show that, starting from the embedding stage, the diameter of the low-dimensional map y of ki1 less than or equal to I less than or equal to n grows fast, and they move in clusters as inherited from the early exaggeration stage. Importantly, over the iterations, the elements of y of ki1 less than or equal to I less than or equal to n belonging to different clusters would in general move away from each other, resulting to an enlarged visualization with more separated clusters. We refer these iteration steps presenting such a drastically expansive and intercluster repulsive behavior of y of ki1 less than or equal to I less than or equal to n as the amplification phase of the embedding stage. We also show that after a certain point, the conditions for the fast expansion phenomenon no longer hold, which likely causes the change of behavior into a new phase which we refer as the stabilization phase. This is in line with the empirical observation, figure 3, that after a few fast expansive iterations in the amplification phase, the speed of expansion amplification gradually reduces towards 0, and in the stabilization phase, the diameter only increases very slowly with the iterations. Figure 3, an illustration of the two-phase of the embedding stage based on the 1600 NIST samples described in section 5. The iterations are counted from the beginning of the embedding stage, and the amplification rate is the ratio between the diameters of two consecutive embeddings. Recall that the updating equation at the embedding stage is C formula, where H is the step size that may not be identical to the one in the early exaggeration stage. To understand the behavior of t-SNE at this stage, we start with the following proposition characterizing the matrix S of k equals S of k ij 1 less than or equal to ij less than or equal to n over the amplification phase. Proposition 12, for any integer k, if diam yk I1 less than or equal to I less than or equal to n equals O1 as n siohari, then for any ij in n such equal to j, 1 if lim n 2 pi j equals 0, it holds that C equation as n plur pi, and 2 if n 2 pi j greater than or equal to C for some constant C bird 0, it holds that of kij as n sub pi. Roughly speaking, Proposition 12 says that over the amplification phase, the matrix S of k equals skij 1 less than or equal to ij less than or equal to n essentially has two types of entries, determined by the magnitude of the corresponding entries in P. Specifically, skij is negative with magnitude n minus 2 if pi j is much smaller than n is 2, and otherwise skij has the same magnitude as pi j. This observation leads to the next theorem, which provides important insights on the updating equation 30 by partitioning the contributions of yki1 less than or equal to I less than or equal to n to an updated y of k plus 1i into a few major components, each corresponding to a distinct cluster in the original data. To this end, we consider again the similarity matrix P that is only approximately well-conditioned, as characterized by the following assumption, T2E. There exists a symmetric and well-conditioned matrix P in Rn satisfying T2D, lim and mighty n2 wes P, lamp P equals 0, and lim nRn in 0, 1 for each R in R. The existence of well-conditioned P-Wes induces an equivalence class on N characterizing the underlying cluster membership. Specifically, for any ij in N, we denote I quina j if and only if the ith node and the jth node belong to the same graph component. Therefore, we have the partition N equals in HR for mutually disjoint sets HR1 less than or equal to R less than or equal to R, with HR corresponding to the rth equivalence class. Next, we make assumptions on the initialization and parameters of h k0 in the early exaggeration stage, where k0 equals k0 n. Glyciscoted is the total number of iterations in that stage. Specifically, we assume I3, the initialization is chosen such that y01 my 2 hit y02 by 2, max n in y0 1 minus through o minus 1 half as n of throide, and there exists some constant c bar 1 such that as I defined in theorem 7 satisfies c minus 1 less than or equal to n z I minus z j y0, 2 less than or equal to c for any ij in R such that I is equal to j and ed in 1 2. And t1.e, the parameters of hkno in 6 satisfy 1 mont d, and for Rn equals 1 minus kira plus hkno, 1 ba n max f in y oda wa 2 o 2 1 of pila minus p, we have nrn 1 plus n boda 1 as n forward. Condition I3 is mild as it can be satisfied with high probability by a straightforward random initialization procedure to be presented shortly. Condition T1E is analogous to but slightly stronger than T1D by requiring a smaller cumulative approximation error Rn between LFK alpha and L and LFHN, that is, more distinct clusters in xi1 less than or equal to I less than or equal to n. Finally, for the parameters h at k1 in embedding stage, where k1 equal n is the number of iterations within the amplification phase, we make the following assumption that controls the cumulative approximation error in sk, as suggested by proposition 12. Dim y plays k1 I can or put 1 less than or equal to I less than or equal to O1, and the parameter h in 30 satisfies k1 apm plus 1 and equal to O1 as n. Theorem 13, intercluster repulsion. Under conditions T1.e, T3e, and I3, for each k nero less than or equal to k less than or equal to k note plus k1 and any I in n, we have C formula, where R is zeroed in R such that I in H are 0, lim in mine f like k I love 2 by qua f of k, I R by 2 equal to 0 for all R in R naro, and C equation. In addition, we have C equation and C equation. A few remarks about the above theorem are in order. Firstly, conditions T1e, T2e, and 3 concerning the initialization, parameter selection, and the number of iterations in the early exaggerations are not only compatible but also sufficient for the previous results, including theorems 4 and 7. This suggests the above intercluster repulsive phenomenon at the embedding stage actually relies on the properties of the outputs from the early exaggeration stage, again yielding the necessity of the early exaggeration, or equivalent techniques. Secondly, as indicated by the next theorem, condition I3 on the initialization can be satisfied by the following simple local random initialization procedure. Theorem 14, random initialization. For any sequence sem n0 as n mare, let y0 equal hat gf hat 2, where ged and rn for independently generated from a standard multivariate normal distribution. Then y0, I1 less than or equal to I less than or equal to n, satisfies condition I3 with probability at least 1 minus the quota for some sufficiently small constant tethered rate 0. Thirdly, the above theorem provides a precise characterization of the kinematics of each yki during the iterations and its reliance on the data points yk-1i in the previous step, as well as the cluster structure inherited from the early exaggeration stage. Specifically, f of k summarizes the contributions from the points yii and hr in the rth cluster to the new point y of k plus 1 I. The theorem implies that, at the amplification phase, the behavior of y of k I1 less than or equal to I less than or equal to n is mainly driven by the relative positions of the R clusters produced in the early exaggeration stage. For each point, a vector sum of the repulsive forces coming from all the other clusters at their current positions determine the direction and distance of its movement of each point in this iteration, figure 2. As a consequence, after each iteration, the diameter of y of ki1 less than or equal to I less than or equal to n would increase till the end of the amplification phase, that is, when condition T3 by E, or more specifically diam y of ki I1 less than or equal to I less than or equal to n equals O1, no longer holds. This process improves the visualization quality by making the clusters more distinct and separated, figure 1 with k equals 40 and 80. Our next result confirms the intuition that the diameter of yk1 less than or equal to I less than or equal to n is bound to increase after each iteration in the amplification phase of the embedding stage. Theorem 15, expansion. Suppose the conditions of Theorem 13 hold. If in addition p min1 n minus 2, then for any k in k0 plus 1, k1, we have C formula. Once the diameter of y of ki1 less than or equal to I less than or equal to n exceeds certain threshold, that is, when diam y of ki1 less than or equal to I less than or equal to n is at least of constant order, we arrive at the final stabilization phase. In this phase, the condition of proposition 12 is violated, and unlike what is claimed in part 1 of proposition 12, the entries of the matrix Sk corresponding to the smaller entries in P, that is, pi j's with pi j n minus 2, no longer remain an almost constant value 1 of n minus 1. In particular, the sign of S of k ij would generally rely on the relative magnitudes between pi j and qij. We rewrite 30 as C formula. In the stabilization phase, the new position for yk plus 1i is determined by the starting point yki and the average contributions from each of the other data points ykj j equals I. The contribution from ykj to yk plus 1i is either in or against the direction of ykj minus yki, depending on sign pi j minus qij. If sign pi j qij equals -1, or the similarity between yki and ykj as measured by qij is greater than the similarity between xi and xj as measured by pi j, the contribution from yk j to yk plus 1i is in the direction of yki minus ykj, resulting to a force that enlarges the distance between yk plus 1i and yk plus 1j after the iteration. Similarly, if sign pi j minus qij equals 1, it means the similarity between yki and ykj is smaller than their counterparts in xi1 less than or equal to I less than or equal to n, so the contribution ykj to yk plus 1i is in the opposite direction, ykj minus yki, resulting to an attractive force that reduces the distance between yk plus 1i and yk plus 1j after the iteration. The iterations over the stabilization phase aim to locally adjust the relative positions of the low-dimensional map to make the final visualization more reliable and faithful. Remark 16. In practice, expansion and repulsion effects help make clusters identified from the early exaggeration step more salient in the final visualization, and possibly more informative in terms of the local structures within the clusters. This is especially helpful if two clusters are positioned too close to each other at the end of the early exaggeration stage, as an artifact of the random initialization, e.g. the middle column of Figure 5. Moreover, the intercluster repulsion phenomenon explains the occasional appearance of false clusters in the t-SNE visualization. Specifically, our theory indicates that false clustering may appear due to an incidental combination of overlapped clusters from the early exaggeration stage with random initialization and the intercluster repulsion from the embedding stage, Figures 5 and 6. This leads to our third general advice on practice at the end of Section 1.2. For Application I, Visualizing Model-Based Clustered Data. In the previous sections, we established the theoretical properties for the basic t-SNE algorithm under general conditions on the parameters AF, H, K1, K2, the initialization, and the similarity matrix P constructed from the original data. In this section, we apply our general theory in two concrete examples of clustered data, one generated from a Gaussian mixture model and another from a noisy nested sphere model. 4.1 Gaussian mixture model. Consider the Gaussian mixture model, C formula, where μr in Rp and PR r equals 1, pi r equals 1. We make the following assumptions. C1, the mixing proportions pi r1 less than or equal to r, less than or equal to r, satisfy minor pi r greater than or equal to c at a 0. C2, there exists some large constant c at 0 such that ρ2 equals min1 less than or equal to j equal to k less than or equal to r mu j minus mu k2 2 greater than or equal to c max p log n. C3, there exists some constant c0 such that the population covariance matrix cells in Rp sines p satisfies c minus 1 less than or equal to line 1, sevas less than or equal to line p less than or equal to c, and tar piana p less than or equal to c. Under the above Gaussian mixture model, we obtain the following corollary that provides the conditions for the theoretical results presented in the previous sections. Corollary 17, suppose conditions C1, C2, and C3 hold, and tau 2I max p log n. If afrobux 1, k at h equals on, 1 to f k known, x im re2 max p log n, and krx 2n log n equals on2, then conditions t1d and t2d hold. If in addition log n k note n minus 1 x p re2 max p log n, k to 2n log n equals on, and k1h equals on, then conditions t1e and t3e hold. As a consequence, suitable choices of the tuning parameters ava h, hh, k to k1 under the Gaussian mixture model can be determined efficiently. For example, if there are 2 log n of max p log n, one could choose k naught equals log n2, h at h equals n that and alpha n1 minus that for any constant that in 0, 1. By corollary 17, conditions t1d and t2d hold, so the conclusions of theorem 7 follows for k equals k0. Meanwhile, conditions t1e and t3e also hold, so the conclusions of theorem 13 hold for each k1 with k note less than or equal to k1 less than or equal to n1 minus thalda. Note that the above results apply to both low-dimensional settings where p equals on and high-dimensional settings where pn. To demonstrate the effectiveness of the theoretical guidance, we generate n equals 1500 samples of dimension p equals 100 from a Gaussian mixture model with r equals 6, 32 equals p, SES equals IP, and the cluster proportion vector 0.1, 0.1, and 0.15, 0.25, 0.3. We use the above tuning parameters with various David and 1/2, 1/30, and perplexity 30 default. The t-SNE embeddings at the end of the early exaggeration stage k equals k0, log n, 2, equals 53, and at k equals 1000 are included in Figure 4 below and Figure 7 in Appendix F, confirming the theoretical predictions. Moreover, Figure 8 in Appendix F shows that when the above separation condition, C2, is slightly violated, e.g. Ray2 equals P45, t-SNE is still able to visualize clusters, which demonstrates the robustness of t-SNE with respect to the separation condition. Figure 4, t-SNE visualizations of the model-generated samples as described in Section 4 using the theory-guided tuning parameters with DA that equals 1/3, see Figure 7 for similar results with DA equals 1/2. The left column shows outputs from the early exaggeration stage, whereas the right column are the corresponding final embeddings. Remark 18, Aurora et al., 2018, analyzed the early exaggeration stage of t-SNE based on a slightly different theoretical framework under the Gaussian mixture model with a mean separation condition Ruhr mix P14 and under the mixture model of log concave distributions with a separation condition Ruhr P512. Compared to these results, our separation condition Ruhr P1 how in C2 is strong. and it is unclear to us if such a restriction is intrinsic to our theoretical framework or an artifact from our proof strategy. Nevertheless, nailing down the sharp information threshold for t-SNE visualization is an important and fundamental problem. We plan to have a more systematic treatment of this in a subsequent work. 4.2 Noisy Nested Sphere Model. Consider the model of nested spheres with radial noise, where for I and n, we have C formula, and I zi equals r, zi I multinomial pi 1 pi r, 38, with PR r equals 1 and pk being uniform distributions on nested spheres in Rp of various radii ρ min equals ρ under 2r equals ρ max. We make the following assumptions concerning the separation distances between the underlying nested spheres, C4. There exists some guy such that max n-1 sems 2d-2 min log n gang guy 1 and max r in r-1, ρ r to r plus 1, 1 minus c square root of gang log guy for some sufficiently large constant c beta 0, C5. There exists some small constant c beta 0 such that c min ρ r plus 1 minus ρ r greater than or equal to 7 square root of log n. In condition C4, the separation distance is characterized by the ratio r plus 1, whereas in condition C5, the distance is characterized by the difference ρ r plus 1 minus ρ r. The following corollary provides a sufficient condition for the results presented in the previous sections. Corollary 19. Suppose assumptions C1, C4, and C5 hold and tau 2 I at 2 zi. If k no h equals on, af r h equal bo n, af r val r plus 1 greater than or equal to key for some constant key in 0, 1, k no o k's 1, af r gon plus 1 swemma 2 and log n equals on 2, and log k no a af n tum gon minus 1 minus max r and er to r plus 1, 2 plus log guy, then conditions t1 d and t2 d hold. If in addition k to a log n, k af av gon plus 1 log n equals on, log k av het va minus 1 minus mar plus 1, dr plus 1, 2 log gon, and k1h equals of guy n, then conditions t1 e and t3e hold. Again, suitable choices of the tuning parameters, ava h jack ko k1 under the noisy nested sphere model can be determined efficiently. For example, let's consider the case where dr plus 1 minus dir equals dadzu die for all r in r minus 1. Specifically, suppose there exists some small constant seed in 0, such that dad greater than or equal to c dri r, and that gangwa equals c of log n minus 1 satisfies I c4 and 1n in probability. Then, by corollary 19, the desired visualization properties, such as those in theorems 7 and 13, would hold with high probability as long as we choose k0 equals log n2, k1 less than or equal to n1 minus that log n, sibin n equals log n minus 2, h equals n david, and af equals gam n1 minus that for any constant david in 0, 1. Figures 4 and 7 in the appendix show the t-SNE embeddings of n equals 1500 samples of dimension p equals 50 at the end of the early exaggeration stage, k equal k2 equals log n, 2 equals 53, and at k equals 1000, generated from model 37 with r equals 3, sim equals 1, ray 1 2 3 equals 10 25 50, and cluster proportion 0.17.33.5. For the tuning parameters, the above analytical values with GAM equals 0.5 and that at in 1/3, 1/2 are used. As a result, clusters of 3 nested spheres are visible in all t-SNE embeddings, confirming our theoretical predictions. Application 2. Visualizing real-world clustered data. Finally, we demonstrate our theory by applying t-SNE to the MNIST-3 dataset, which contains images of handwritten digits. Specifically, we focus on n equals 4 in equals 1600 images of handwritten digits 2, 4, 6, and 8, with each digit having n 400 images. Each image contains 28 times 28 pixels and was treated as a 784-dimensional vector. Based on our theoretical analysis, we set the tuning parameters, see formula, with that at equals 230. Again, we use the default perplexity equals 30, leading to an approximate block matrix P with block structure corresponding to the cluster membership, Figure 9. Figure 5. Illustration of t-SNE embeddings of 1600 MNIST samples at the end of embedding stage, bottom row, and their corresponding outputs from the early exaggeration stage, top row. Different columns have identical initializations and tuning parameters, but distinct number of iterations for the early exaggeration stage. The colors of the dots indicate the underlying 4 clusters. To demonstrate the necessity of stopping early at the early exaggeration stage, in Figure 5, we show the t-SNE embeddings at the end of embedding stage, bottom row, and their corresponding outputs from the early exaggeration stage, top row. Different columns have identical initialization and tuning parameters, but distinct numbers of iterations for the early exaggeration stage, namely K0 equals log n2 equals 54, left, K0 to 137, middle, and K0 n3 forward equals 253, right. Comparing the top three plots in Figure 5, we can clearly see that when K0 far exceeds our theory-guided value, log n2, the cluster patterns is no longer visible, which, in the case of K0 equals 253, led to false clustering in the final visualization. Moreover, the middle column of Figure 5 also demonstrates the importance of the embedding stage, especially its underlying intercluster repulsion and expansion effects, as to making the cluster patterns more salient in the final visualization. Figure 6. t-SNE visualizations of 1600 MS samples based on 3 different random initializations and identical tuning parameters in 39. Next, we assess the effects and artifacts of the random initialization. In Figure 6, we fix all the tuning parameters as in 39 and generate t-SNE visualizations from 3 different random initializations. Comparing the first 2 plots, we observe that the relative positions of the clusters vary with the initialization. For example, the purple cluster and red cluster are neighbors in the left panel, but not in the middle panel. This echoes our theoretical prediction, discussion after Theorem 7, and justifies our second practical advice in Section 1.2. On the other hand, on the right panel of Figure 6, we find that even with a proper choice of the tuning parameters, false clustering may still appear as an artifact of the random initialization. Cf. Remark 16 and the third practical advice in Section 1.2. Finally, we point out that our theory-guided values for the tuning parameters are flexible, robust, and adaptive to the sample size. For example, in Figure 10, we present 3 more visualizations of n equals 2400, n equals 600 for each digit, MNIST samples, by using the tuning parameters in 39, with various theta in 1/3, 1/2, 2/3, and an identical random initialization. The cluster patterns are visible and similar in all the cases, showing the effectiveness of our tuning parameters and the insensitivity to the choice of theta. 6. Discussion. The present paper provides theoretical foundations of t-SNE for visualizing clustered data and obtains insights about its theoretical properties and interpretations. We believe that some of the conditions may be relaxed by adopting more advanced technical tools. For example, the current analysis of the early exaggeration stage relies on the well-celebrated Davis-Kahan matrix perturbation inequality, cf. Section B3, which may be further improved by leveraging advanced results in random matrix theory, such as Benesh, George, and Nadakudity and Bao et al. There are still many interesting questions that remain to be explored. For instance, what is the limiting behavior of the low-dimensional map, y of ki1, less than or equal to I less than or equal to n, towards the end of the embedding stage, after transition to the stabilization phase? How to interpret the local structure within a cluster? How many iterations are needed for the embedding stage? How to determine the bandwidth tau I in a data-driven and adaptive manner? The present work is a first step towards answering these important questions. Moreover, our theoretical framework is generic and can be generalized to study other algorithms that are closely related to or share similar features with t-SNE. For example, in addition to the variants of t-SNE mentioned in Section 1, many dimension reduction and data visualization methods, such as multidimensional scaling, kernel principal component analysis, and Laplacian eigenmap, start with a similarity matrix summarizing the pairwise distances within a dataset, and then proceed by either explicitly or implicitly exploiting the spectral properties of the similarity matrix. In this connection, the general ideas behind our theoretical analysis, such as identifying the underlying structured graph and properties of its adjacency or Laplacian matrix, sections 2.1 and 2.2, studying the gradient flow associated with the discrete algorithm, section 2.3, and the mechanical kinematic view of the updating equation, section 3, can be adopted to uncover the underlying mechanism and the properties of these methods. It is also interesting to explore the fundamental limit for data visualization and dimension reduction. For example, What are the necessary conditions for the data xi1 less than or equal to I less than or equal to n to guarantee the existence of a low-dimensional map, yi1 less than or equal to I less than or equal to n being a metric embedding of it? Whether t-SNE has to sacrifice some global structures in order to locally embed the data well. These problems are left for future investigation. Acknowledgement. The authors are grateful to the editors and 4 anonymous referees for their comments and suggestions, which have significantly improved the results and presentation of the paper. The research of Tony Kai was supported in part by NSF Grant DMS 251259 and NIH Grant R01 GM 129781. The research of Rong Ma was supported by Professor David Donahoe at Stanford University. This work was partially completed while Rong Ma was a PhD candidate in biostatistics at the University of Pennsylvania. Rong Ma would like to thank Mingyao Li for introducing the subject, and Michael Aupetit, David Donahoe, Jeong Li, Stefan Steinerberger, Yiqiao Zhang, and James Zhou for helpful discussions. This concludes the reading of Theoretical Foundations of t-SNE for Visualizing High-Dimensional Clustered Data on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.